The first question of homework 1 is that the two uniform rods of mass m and length L is welded together to form T shape, which is shown here. Determine the natural frequency of the small oscillation of this assembly. So for this, first we have to get the what is the mass moment of inertia of this system about point A. So about point A, the moment of inertia is moment of inertia of first rod and the moment of inertia of the another rod about point A. So the rod AB, the moment of inertia is ml square by 3, and for the rod CD, the moment of inertia is ml square by 12 plus ml square, that is mr square. It is acting at distance of L from point A. So rod CD is at a distance of L, so the ml square. So the total is 17 by 12 ml square. So now if we reflect at an angle of theta the rod about point A, so for the small oscillation, the weight of the rod, first rod is acting downward, mg, at a at a distance of L by 2 sine theta, as the rod half of the rod is L by 2, so it is acting at L by 2. So the distance from the point A, and CG is L by 2 sine theta, and the second rod, for the second rod the weight is also mg, so this is also acting at a distance of L sine theta. This one is the L sine theta. So the moment about point A is mg sine theta, mg into sine theta L by 2, and second one is mg into sine theta L. So for the small theta, sine theta is equal to theta. So the rearranging, we will get m minus of mg theta 3L by 2. So the equation of motion is ja theta double dot is equal to summation of moment summation about point A. So we have already moment of inertia about point A, which is 17 by 12 ml square theta double dot is equal to minus mg theta 3L by 2. So by rearranging, we will get the theta double dot plus this is omega n square into theta is equal to 0. So the omega n, so the natural frequency of this smallest oscillation is 1 upon 2 pi under root of 18 G by 17 L. So the second question of homework 1 is a slender uniform rod of mass m is pivoted at the bottom end and is held equilibrium by the two springs. What is the natural frequency of the vibration for the small amplitude? So this is a rod which is the end is pivoted here, and it is equilibrium by the two springs with same stiffness K. So first we will get the what is the free body diagram for that, so that we can consider for the get the natural frequency of that for the vibration, for the small vibration. So first we can see that here, if we give the small vibration, some small deflection of angle theta, and so that the weight of the rod mg is acting downward, and because of the small deflection theta, we will get the restoring spring force of yes is equal to kx. So x is the small displacement, which is x is equal to L into theta. So L is the length of the rod, and theta is the small deflection what we are getting. So the weight of the rod is acting downward, so because of which we can calculate the spring forces and the spring forces. So again again we are going to apply the second law of motion for the swinging rod. So J double dot is equal to summation of moment about so so taking the moment about this point O. So the sum of the moments is induced by the force at point O. So the force because of the weight of this rod and the spring force. Spring force is acting in this direction and weight is acting downward direction. So for Jo theta double dot is equal to the force due to weight into L by 2 sine theta. So this is the length L by 2 sine theta, and the spring force is acting in other direction. So the spring force into L cos theta. So it is the length, and this is the L cos theta. So and the moment of inertia of the rod about O is ml square by 3. So theta double dot is equal to mg into L by 2 sine theta minus 2k x. So x is L theta, spring force is 2kx because two springs are acting, so 2kx. So x is L theta, so we will get this one into L cos theta. So we know for the small angle theta, sin theta is equal to theta and cos theta is equal to, we can assume, is equal to 1. So again rearranging this equation, so we will get theta double dot plus 6k by m minus 3g divided by 2l into theta. So this is our omega n square. So we can get the for the natural frequency divided by omega n by divided by 2 pi. So we will get this one 1 upon 2 pi under root of 6k by m minus 3g by 2l. So this is the natural frequency. So the third question of homework 1 is that determining the natural frequency of the horizontal pendulum is shown here, neglecting the mass of this arm. So here the L-shaped arm is here, which is at the bottom is attached with a spring, and the other side is attached with the mass m. So for this, if you give the small rotation of angle theta, so because of which the spring force, the spring will extend, so because of which spring force Fs will act here, because of which the equation of motion we can get for this dynamic system. So for that, taking the equation of motion about this point O, so at this point O, the force so the spring force is X is equal to Fs is equal to K into X. Here X will be the A theta. So so this spring force into A cos theta, which is acting at A cos. This spring force is acting at A cos theta. So at A cos theta, and the Jo is for the rod is mb square. Mass of the rod is acting here and at a distance of b, so mb square. So if we take rearranging this equation, we will get the theta double dot plus ks square divided by mb square. So this is omega square is equal to ks square by mb square. So the natural frequency we will get this one, 1 upon 2 pi a by b under root of k by m. So you also can think that because of this mass, why we are not considering this mass in this equation of motion. So we will consider the detailed force analysis. Why we are not considering the mass for this equation of motion. So for the weight does affect the induce the static deflection but does not affect the dynamics. So for this one is we are considering the dynamic analysis. So for the static analysis, so moment about O, if you are considering moment about O, so is equal to 0, taking the moment about O is equal to 0. So the weight is acting, the weight mg of this box is acting downward, and which is acting at a distance of b cos at an angle, suppose psi, at an angle of psi. So it is acting at b cos psi, because of which as it is at an angle of psi, so because of which the another force, spring force K A psi is acting here. Okay, so K A psi. So so we will take moment about O is equal to 0. So for the small angle we can cos psi is equal to 1 and cos psi is equal to 1. So we will get psi is equal to mgb by K square. So this one is for the static analysis. We will get the angle psi. Again, so if we are considering the now we are considering the dynamic analysis, which is due to the weight psi plus angle theta that we are deflecting. So for this dynamic analysis, for this equilibrium position we can consider horizontal or vertical. So that taking moment about O, so Jo theta double dot is equal to take moment about O. So this one you already know. So again, this weight acting downward, so mgb cos theta, now we are considering angle theta, minus of Ka, the angle is total psi plus theta. So psi we are considering for the static deflection plus theta into a cos theta, that is acting at a distance of a cos theta. So this is for the this is the force due to spring extension, due to spring force. So now we know the value of psi is mgb by K square. If we put here, so we will get again the same equation that we are obtained previously, this one in the dynamic analysis. So whenever we so we can directly neglect the weight of this box. So in this dynamic analysis, and we can get the equation for the natural frequency. Now the fourth question of homework 1 is that the mass m is suspended from the spring with a modulus k, which is in turn suspended at its upper end from thin steel cantilever beam with a thickness t, with w and the length l. The cantilever and the spring have the negligible masses. So the cantilever and spring have the negligible masses. Determine the natural frequency of the weight's oscillatory motion. Okay, so in this case, here we can consider here are two springs, one due to the cantilever rod and another one is this spring. So for the cantilever rod, we have deflection of the cantilever rod. If we are acting if the weight is hanging at the end of the cantilever rod, we have the deflection of the cantilever rod is delta B is equal to FL cube by 3EI. F is the force acting in the downward direction here, length of the rod, and divided by 3EI, where I is WT cube by 12 for the width and thickness. Okay, so the stiffness of this cantilever is KB is equal to force divided by deflection. So we can get the 3EI by L cube is the stiffness of this cantilever rod. Now we have the both stiffness When K is the stiffness of the spring, and KB is the stiffness of the rod. So this system, the springs in these systems are in series. So the effective stiffness for the two spring in the series are 1 by K plus 1 by KB, 1 upon 1 by K plus 1 upon KB. So is equal to, we will get K KB divided by K plus KB. Now we can consider the equation of motion. So this case mx double dot is equal to minus K effective. Now we will consider the effective spring stiffness into x plus delta. Delta is deflection due to, so mx double dot is equal to minus K into effective in bracket x plus delta. Delta is the deflection due to this mass mg mass that we are attached here in the to the spring, because of which we will get the total deflection is x plus delta because of this mass mg plus mg. So here we can consider here mx double dot is equal to minus K effective x minus K effective into delta plus mg. So this one is the static analysis. We already know that mg is equal to minus K effective delta. So we can directly so this one becomes 0. So mx double dot is equal to minus K effective into x. So by rearranging, we can get the mx double dot plus K effective into x is equal to 0. So the natural frequency of the will be the K effect under 1 upon 2 pi under root of K effective by m, because omega n square is equal to K effective by m. So we know the value of K effective. K effective is K KB divided by K plus KB. So this one is the natural frequency of this system. So the fifth question of homework 1 is a heavy table is supported by the flat steel legs. Its natural period in the horizontal oscillation is 0.4 seconds. When 30 kg plate is clamped on the surface, the natural period in the oscillation is increased to 0.5 seconds. So what is the effective spring constant and the mass of the table? So there are two cases. One is case without the mass of the plate, and another is when the plate is clamped on the surface of the table. So let us consider both the cases. First case is, for the first case without the mass of the plate, we'll consider the equation of motion. So for that simple case, the mx double dot plus kx is equal to 0. K is the spring constant for this steel legs. So the natural frequency is 1 upon 2 pi under root of K by m. Now the second case is when the 30 kg plate is clamped to the surface of the table. So the mass is increased from m to the m plus 30 kg, and the stiffness of the leg is the same. So the m plus 30 kg. So the equation of motion is the m plus 30 kg into mx double dot plus kx is equal to 0. So the natural frequency becomes 1 upon 2 pi under root of K by m plus 30 kg. Now the natural period of the oscillation can be derived from the time period. So we have the natural period for the case 1 is 0.4 second when the 30 kg plate is not clamped. So for that time period is 0.4 second. So we can get 0.4 second is equal to 2 pi under root of m by k. When 30 kg plate is clamped on the surface, so the time period is 0.5 second. So for that also we will get the equation. So comparing these equations, equation 1 and equation 2, uh, taking the ratio of these two equations, we will get Ta by Tb is equal to under root of m by m plus 30 kg. So so now we know the time period for the case 1 and time period for the case 2. So from that we can get the mass of the plate is 53.3 kg. Now for the effective spring constant, we can consider any equation for the case 1, case A and case B. So let us consider the case A. So in this case a time period is 0.4 second. We know the mass of the table. So if we put the mass of the table in this equation, we will get the effective stiffness, which is 13154 Newton per meter.